Okay. So this is still quite ongoing and we're still working on this. So this is going to be more of like a status update as to where we've reached in the project as opposed to a full results and analysis. So here's briefly what I'll talk about. So we're comparing three different sort of techniques to solve the Kohn-Sham equation. And I'm going to first sort of introduce those three techniques and then basically talk about how we compare and some of the results we've got and sort of the initial analysis that we've been doing and what next steps that we plan to do. So I'll start with the KKR Green's function method because that's what we're doing in the must code. So KKR method is not interested in finding the block wave functions. You're only interested in finding the Green's function of the system. And if you find the Green's function of the system, you can take the imaginary part and you integrate with respect to energy. The Green's function has poles on the real energy axis, so you make a contour and then you integrate along that contour and you can get your charge density. If you integrate with respect to space, you get density of states. If you multiply any operator, if you act any operator on the imaginary part of the Green's function and integrate, you get the expectation value of that operator. So essentially the imaginary part of the Green's function contains all information about the system. And the sort of technique to do this, the most important part is to divide the system into atomic cells. So around each atom, you define a cell, and within that cell, you calculate, just for that one atom, you calculate the solutions of the Schrodinger equation. You calculate the T matrix. You calculate what's called the tau matrix, which is basically multiple scattering. You're calculating all the possible paths of scattering between, say, atom 1 and atom 2. And then you can put that together with the single site solutions to get the Green's function, the local Green's function around each atom, and then you can get the local density. So that is basically how the KKR method works. Now, there's also another method called the APW method, or the augmented plane wave approach. Now, it's similar to the KKR method in the sense that it also considers individual atoms cells. So you create the muffin tin sphere around each individual cell. Now, within that cell, you assume that your solution has this form. Indeed, you can of course write any function in terms of spherical harmonics as in a sphere that's a complete basis. So you write your solution in this form, and in the interstitial region, you write your solution as a plane wave. And using boundary conditions at the muffin tin sphere, you can find your coefficients A and B. And your overall wave function will then be a superposition of all these 5 wave functions. And then this is your sort of fictitious wave function that you constructed. And then you can optimize for Cn by using the variation principle. So it's similar to Green's function method in the sense that you are still dealing with atomic cells. You are solving for all electrons. So this is an all electron method. So you will get solutions for core electrons as well. But you solve for the wave function and not the Green's function. And while KKR method gives sort of the realistic Green's function, so that is the actual Green's function of the system. This is more of a wave function, more of a construction, and that you optimize using a variational principle. So that, and the code, the popular code that uses this approach is Wien2K, which is the code that I've used that employs this method, like must employs KKR. Also, a natural question that extends is, why do we need to augment the plane waves at all? Why can't we just use a plane wave everywhere in the system? Because a plane wave basis can, if you take enough basis elements, can also be complete. So why not use plane waves everywhere? And that's because if you look at the charge density, sort of, it's very sharply peaked near atoms. So your potential is quite sharply peaked. So very close to an atom where the core electrons if you solve a core electron states, you're going to need a lot of basis elements. And even say solving the Poisson equation also can be difficult with this potential, because normally you solve the Poisson equation using Fourier transform, and Fourier transforming a very sharp function would require a lot of frequencies, because if you have a sharp function in real space, its Fourier transform is very flat and it has a lot of frequencies. So, and also this wave function has quite oscillatory behavior as the potential peaks. So it's really
Vishnu,
not practical.
just one short question, Vishnu.
Yeah.
Since in signal processing, people also face typically the problem that the function has jumps or spikes, and the way they deal with this in signal processing is they use wavelets as a basis as opposed to waves, plain waves. So has anyone tried to use wavelets for the core states?
Yeah, it's the second. Oh, it's my yeah, it's on. Yes, people have used wavelets. Yeah, there are wavelet codes around. Yeah. In fact, there were people that use wavelets at the lab, so it's been a sort of methodology that we thought might be interesting, but we never really took it up to the stage of having these codes. Well, got enough on our plates with KKR, right? So.
Let's see. Okay, great. Thank you.
Yeah, so
wavelets can be a bit tricky with regard to either orthogonality or differentiability. I mean, it's very hard to construct a smooth orthogonal wavelets.
Yeah, that's right. If you use for the wave function approach, not only you have to solve the wave function, but you have to also to do orthogonalize and normalize the wave function. So it's become more complicated.
Yeah, so one other approach, basically, the idea behind the pseudo-potential.
Can I just say one comment? I mean, so it's not really been mentioned, but one of the problems of electronic structure theory of this kind, it obviously goes back a long time, and one of the things that if you depending on your basis set, the question as to how many of these functions do I need in order to accurately represent what's going off, and you put more and more and more in, and if you're not very careful, you get to the situation where adding another wave function makes things worse, right? And and that crops up, and a lot in the original days, and that's one of the things that drove things like the pseudo-potential, to avoid having to put all of these wave functions in that did nothing other than deal with the core, and in fact require a lot of functions in order to be able to describe what's going off well. So that's probably more than enough. Sorry.
Thank you very much, Mark.
Yeah, so basically the idea here is with the pseudo-potential is to not deal with the core electrons. So essentially you construct a sort of fictitious potential that is meant only to deal with your valence states, and you deal with the core electrons separately and you store it elsewhere. And when you solve, when you use the code, it only solves for the valence states. And in that case, you get rid of your oscillatory function problem, and you get rid of the core electron problems, and then you can use a plane wave basis everywhere. And then the number of plane waves needed is also not too much. And the popular code that uses this, of course, is VASP. and the energy cutoff or n cut parameter in VASP is basically the number of basis functions that you need to describe it well. And since you're not, unlike the other two methods, this is not an all electron method since you're not solving for the core. So our project, the aim was to check whether all these methods are consistent. And a more specific question that we asked is to look at one parameter, which is total energy, and to see if the total energy values obtained, say, for the same set of systems, are they consistent? And of course, the first question that I had is, how does it matter if they're consistent or not? Let's just look at the approach which seems most accurate and seems most likely to give the most accurate results, and let's just use that method. And but that's not, so the idea is different methods have different advantages. So the KKR Green's function, if you combine with CPA, you can very efficiently deal with random systems, and that kind of efficiency you won't get from the other methods. And you can also have very precise control over concentrations. So because in a supercell approach, if you want to specify concentrations and you want to have more precise control over concentrations, you need larger and larger supercells. But in CPA, you can, in that file, just specify, I want copper to be 0.512 and zinc to be minus 488. So, and whereas if you want to do that to the supercell, you'd have to create 1,000 atoms, and 512 atoms have to be copper and 488 atoms have to be zinc. So there are basically advantages to certain methods. And we wanted to use KKR CPA total energies to study the order disorder transition in copper zinc and other systems. We wanted to use first principle instead of using an Ising model type Hamiltonian, which is generally used in to study these order disorder transitions. We wanted to just use first principles energies directly by just giving a concentration and getting KKR CPA energies, and then using an entropy model and getting transition temperatures. But in order to do that, we need to make sure that the energies that you're getting from KKR are consistent with energies you get from, say, VASP and other methods. So that's what we want to check. And so here's sort of the setup. So if you have 16, so we created a 16 atom BCC binary structure. And those binary structures are among chromium, molybdenum, niobium, and vanadium. And there are 59 different possible structures of basically 16 atom decorations that you can create. But we sort of handpicked, we did energy calculations for all of them, and we looked at the symmetries, and we picked six structures that we thought were least and most stable and also had interesting symmetries. So for these 6 structures, we thought we would calculate VASP, VN2K, and MUST energies and see how well they compare. So out of the 6 binaries, I'll present these 4 first. So here I have 4 data sets in each of these 4 plots. I have VASP, I have VN2K, and I have basically MUST KKR applied using muffin tin approximation, where you have a spherically, you assume that your potential within the muffin tin sphere is spherically symmetric. And we have a full potential KKR, where you don't assume spherical symmetry. And it can be seen that for these 4 systems, there's a vast disagreement between muffin tin and full potential. But when we did the other 2 systems left over, which is chromium, vanadium, and molybdenum, niobium, we find that the muffin tin actually agrees quite well with full potential. And all 4 of them agree with each other to an acceptable degree. So this seemed a bit confusing as to why.
So Vishnu, just to understand fully, the other 3 methods other than the muffin tin are the agreement is generally excellent, and so, but the KKR version is CPA. The other ones are not CPA, or this is just a periodic structure, and you're just comparing different band structure methods. I got lost there.
No,
there a
there's no there's no
there's no
CPA. It's
CPA.
all
There's
yes.
okay,
These,
okay. No, okay.
so
Now
these are all
now
yeah. So we are only looking at perfectly ordered structures.
right. So there's no averaging over these different structures. This is
No,
just
no.
for each structure. Okay, thank you. Sorry.
Yeah. So basically, I have each structure, and I'm looking at energy taking off the averages just to put them on a similar scale. And here you can see that there are muffin tin sees more fluctuation among the different structures than the other methods, which all seem to agree well. So
One question I have looking at this, I noticed that structures 3 and 4 have, in the muffin tin case, the best agreement with the full potentials and the others are off. Is there something in the symmetry of those that would suggest that they should be, that the spherical approximation should be better?
I think this is so that part is I think slightly misleading because I have taken off the averages, and the average energy for the muffin tin is a bit different than the average energy for full potential, because in this case I was interested in looking at the fluctuation from the mean. So the fact that these two look similar seem close in terms of averages because that's basically an artifact of taking off the average. So I'll get to the symmetry part essentially in the next few slides, because symmetry does play an important role, but it is not the case that 3 and 4 are more spherical. So that's basically the confusing part for us as to why it works well for certain systems and it doesn't work well for other systems. And to look at that, we have to see what the potential is actually in the KKR code. And the potential is expressed in this way. You have a spherical part of the potential, which is what muffin tin part deals with. And then you have an angular part, which is expanded in a spherical harmonics basis. And this is what is written out in the output in the potential file when you do a must calculation with KKR. And this information can be extracted from that output potential file. So basically, there are a lot of LNMs. So we're looking at up to L equal to 8. So there are about 45 terms here. And I was interested to look at how many of those 45 terms actually contribute to the potential. And I set, as an initial test, I set a threshold where if for any of the LM, there is at any point, any radial grid point for any atom, there's if the absolute value is greater than 10 to the power minus 4, I consider that particular VLM will contribute, and I consider that, and I ignore anything that doesn't satisfy this criteria. And then I made a table of the number of LM components that actually contribute. And it can be seen that if we go, say, along from top to bottom for a single structure, say S1, it does seem that there are less angular components, angular VL coefficients that are contributing for the chromium, vanadium, and molybdenum, niobium, as opposed to the other 4 structures, which seems to give the impression that there's more angular dependence in the potential for those 4 structures where muffin tin wasn't agreeing well, as opposed to these structures. And if you go just for a single binary along the row from S1 to S6, it can be seen that the S6 structure is actually has the least number of angular components. And that actually makes sense because S6 is CP2, and it is the cubic structure. And here, if you don't take off any averages, if you just look at the energies, which is what I put here for the chromium molybdenum structure using muffin tin and full potential. You can see that there's the least difference in energies between muffin tin and full potential for S6, and there is most disagreement for S1, and that sort of ties in with the number of angular components that you see here. There is this anomalous S4 part which seems to have more number of components. But apart from that, there seems to be some correlation here. And we're currently investigating more to see. So another idea is to, instead of having a threshold, to take sort of integrate along different, along all the angular, along all the radial grid, and see which integrated value is the most, and that might contribute more. Another idea that we're exploring is to take off the cubic parts. So this S6 component has only the 8 cubic LM indices, which is, if I can remember correctly, 0040446064. So if we can take out the cubic part, we can find out which in which way the spherical harmonics combine to create cubic symmetry, and take those out. Then what you have left will be the non-cubic part. And then if we then look at which has the most non-cubic part, that might correlate well with the energy mismatch. So those are some approaches that we're currently looking at. One thing also is to look at the, actually plot the VLMs. So for the different, these different data sets represent the different zeros, and since there are quite a lot of them, for example, there are 25 of them, so I haven't put the labels in the legend bar because there's quite a lot. So one thing that I noticed was basically this looks similar. So if you look at chromium, the one for a chromium atom, this is what the potential for the chromium atom looks like, regardless of which binary it is in, whether it's chromium molybdenum or chromium vanadium. So this seems to be an atom-centered property, and the sort of profile looks similar for chromium and vanadium, and it looks similar for molybdenum and niobium. And I think this may give some intuition as to why, say, chromium vanadium agrees well and chromium molybdenum doesn't. I mean, I'm still not really sure exactly how I can connect this to the total energy, but this is something interesting that I thought was worth putting. So that is, so all the data that's basically I have right now, and trying to see if I can get more information from the potential data. We also have charge density, which is not printed out in the potential file, but is available in the code. So I can extract that and then look at the angular spread of the charge density to see if there is more, say, angular spread in chromium molybdenum structures than, say, in molybdenum niobium. We also have a set of FCC structures that we obtained from, instead of chromium, molybdenum, niobium, and vanadium, we're looking at, say, copper, palladium, nickel, and silver, and doing a similar thing, but looking at FCC structures. So I am currently doing energy calculations for those, and we'll get along to doing an analysis for that. Also, we still haven't answered the question of why it's preferred along a row. So say chromium, vanadium, molybdenum, niobium are elements that are next to each other on the periodic table. So they have an atomic number difference of only 1. Whereas the stuff that doesn't agree with each other is chromium, molybdenum, which is along the same group, which is confusing because elements along a group should behave similarly because they have same number of valence electrons. So it is still somewhat a matter of confusion why things agree well when you have the two atoms that are along the same row, but not along the same column. One idea is maybe because we're looking at an all electron potential, it's not just the valence electrons that matter. Maybe it's because the entire atomic number matters. And even though chromium and molybdenum are along the same column and they have the same valence electron behavior, the atomic number is still vastly different. So whereas for chromium and vanadium, which are next to each other, they have similar atomic number. So maybe that's one argument, but that's sort of along the lines I'm thinking of and trying to see if I can find some data to support that. Also, I'm also doing full potential semi-core calculations. So right now in MUST, the calculations I've done, the semi-core states have been treated using the muffin tin. And I'm doing some full potential semi-core to see if I can get even better agreement between the KKR, VASP, and VN2K. So that is basically the point at which the project is right now.
So what stage is the code in with respect to taking care of the semi-core states in in a consistent way as with the valence states?
It can. So the code is currently capable of doing a full potential treatment of the semi-core states without having to create a big contour. So that
You're using these tricks that Jan told us about in the past. Is that what's happening?
Yeah.
Okay.
You have to create the small contours near the poles of the real energy axis.
Yeah.
So I'm currently doing those calculations and trying to get them to converge.
Yeah, I mean, I think that's the way to do it, and I think you're precisely right that that's going to cause the fact that those semi-core states are not taken into account properly is probably a problem. Of course, the further down you go in a column, the bigger things are getting, right? And so some of those semi-core states presumably figure in a very accurate calculation of the total energy, which incidentally is exactly what the pseudo-potential throws away, right?
Yeah. Some of those semi-cores, like in VN2K, they treat it as valence, as part of band structure. So basically, by implicitly, that means that they're treating full potential with it. So we have to do something.
Yeah, that's basically. Yeah, I mean, just a second. Just to say, I need to turn the. Oh, it's gone off of the telephone. Yeah, I suspect that it's just the. Yeah, so the further you go down, but again, what you have to worry about is that as you go down the series, wait. No, I don't want to do that. That's a relative. I was thinking of something, and it's a relativistic effect, not a non-relativistic effect. So all these codes, you're running them in the non-relativistic way, right? Okay, good. So you're comparing like with like.
Yeah, non-relativistic.
So the Lmax that you go to for all of the, so what I sort of a little bit, maybe I wasn't paying attention, that you said what the Lmax was for the potentials and for the wave functions. And do you test that they are in fact converged by adding yet another one?
Yeah, I tried going from, I think 4 to 3 to 4, and there was some slight improvement. And then I think we went from 4 to 5.
Yeah.
And it's 2 times, so I've set it as 4, but the actual Lmax is 8.
Okay.
Yeah.
Okay, I'll stop recording. So guys.